All right, CNT120, we're working on Chapter 4, and we just talked about the beginning part or the basics of routing protocols. Now they're going to talk specific routing protocols. And just remember, this is routing protocols. Their job is to build the routing table that the routers are going to use to make decisions. So when a packet shows up on the doorstep of a router, the router is going to consult the routing table to decide what port it goes out. So the routing protocol is really there to help build the routing table and update the routing table. So the first one they talk about is RIP, which routing information protocol. This is an interior routing protocol that's a distance vector. And the name actually kind of tells you what it's doing. It's going to maintain in its routing table how far away a network is by using what's called a hop count. The hop count metric, all it is how many routers away. So it's real basic information. It's kind of like saying, well, it's 10 miles away, but you're not getting any information on the quality of the roads. So this is like, well, it's 5 routers away. Well, how much distance is between them? What's the bandwidth? So it's a very basic metric, and it's a very basic one for routers to count and share. If you told me it's 4 away, I'll add 1, make it 5, and tell my neighbor. So it's a very basic metric. RIP uses what's called hop count as its metric. It's going to broadcast this routing table on a timed basis, typically like 30 seconds. Every 30 seconds it's going to broadcast this routing table to all of its attached neighbors. Well, routers don't pass broadcasts, so when it broadcasts it out, the neighbors get that, stop it, they don't pass it. They pick up that routing table information, add it to theirs, and they turn around and do the same thing. So this is creating a lot of excess traffic on the network because all the routers are broadcasting every 30 seconds. Here's my table, here's my table, here's my table, okay? In addition, the convergence time for this is slow because, think it through, if a router gets a change, it's going to add it to its table, and then in like 30 seconds it's going to broadcast out. That next router is going to pick it up, add it to its table, and in about 30 seconds broadcast it out, and so forth. So, if you just use simple math, if you have a couple routers away, it's like 30 seconds plus 30 seconds plus 30 seconds plus 30 seconds. It's going to take a minute or two for a change to get sent through the network. So it's a very slow convergence time by doing this broadcast and routing table thing. The hop count is limited to 15 hops because of this whole broadcasting and passing routing tables and so forth. That's there to prevent routing loops. And this does not work well in large networks. Yeah, that's why it's kind of an interior gateway protocol used for, smaller networks inside my company, if you will. Many places don't use this anymore. There's better protocols out there. Here's a sample RIP routing table. This is actually from one of the labs we do. I looked after the students hooked up their networks. We look at the routing table, and here's a super basic RIP routing table. And I took one of the lines on here just so you could see how it decodes. The C are, over here, the code of C is indicating this network is directly attached. So directly attached to the network is a 192.168.10 network out the fast Ethernet port. Fast Ethernet 00, and the 10.0.0.0 network is directly connected out the Fast Ethernet 01 port. So the router knows they're there, and it's like, awesome. I know exactly where they are. It now learned about, through RIP, the 172.16 network, and it says, oh, okay, I'm going to get to that network by going out this Fast Ethernet 01 port. I'm going to go to this IP, which is the IP of the next router, if you will. I'm going to go to this IP, and it's going to be one router away. That's what the 1 here is. And I should be able to get to this 172.16 network. That's how I'll get there. And if you look a little closer, you'll see the 120. There's that administrative distance for RIP. Okay, so there's real quickly a RIP routing table and looking at the information it maintains. This is all it maintains to make path decisions. Like I said earlier in our earlier podcast, it's maintaining networks and kind of where they're located or how to get to them. This network out this port. This network out this port, 1 router away. This network out this port. Okay, so there's RIP. OSPF, Open Shortest Path First. A lot of places tend to use this routing protocol because it is an improvement over RIP. OSPF is, again, another interior gateway, but it's a link state. So it actually is going to use a little bit better metric. This was introduced as an improvement to RIP. It does support larger networks. It does not impose a no-hop limit. It can handle larger networks. It uses a more complex algorithm, and it's usually a cost metric based on bandwidth. So it actually factors in how far away something is as well as the bandwidth. So the cost metric, you notice it's in quotes there, is a factor of those. It's almost like having a mathematical formula that I calculate how far away it is and the bandwidth, multiply it together, and I get a number. So the higher the number, the worse kind of thing. That's the idea behind it. It's going to demand more memory and CPU on the router to process all of this. It really does. But the trade-off is it's going to use what are called link state routing updates. It really is only going to send out these updates when a change has occurred. And it's going to, instead of broadcast, it's going to multicast all the routers. The idea there is, with a broadcast that had to go to a router, that router stopped it, and then it broadcast to the next router, and that stopped it, then it broadcast to the next router, and that stopped it. So it was kind of a very choppy way to get the information out with the broadcast. With multicast, this message is designed to go to all the routers, I'm putting this in air quotes, all the same time. Multicast is it's going to go out to all the routers, and theoretically all the routers are going to receive that information, at the same time, if you will. A lot faster convergence time than your distance vector RIP. All major router vendors support this, but it is limited to IP4 networks. But a lot of places do use this. In our second level networking class, we use RIP for like the first lab, and from there on out we use OSPF because it is very common. A lot of places use that. So here is an OSPF table from one of the labs we did. Again, if I take a look down here, this is maintaining networks, what port. So if I take a look, this 192.168 network is out this port, this 10 network is out this port, and the 172 network I'm going to get to out this port, fast Ethernet 01, via this IP, so that's the IP of the next router. And I'm going to get there, it's not 11 hops, that's a cost metric. That's distance and bandwidth factored together. Okay? So, 11 would be better than 22, so to speak. And then there is the administrative distance, 110. Remember, that's a lot better number than 120. That's better information than 120 of RIP. Administrative distance of 120 for RIP. So there's decoding an OSPF routing table. Again, the router's maintaining networks and how to get to them. Networks and what port I'm going to use to get there. ISIS, intermediate system to intermediate system. This is another link state, interior again. It uses a best path algorithm similar to OSPF. It is designed for use on core routers only, unlike OSPF. It's able to adapt to IP6, so this might be one that people are migrating to here soon. And service providers generally prefer this because it is more scalable than OSPF. So a little bit better than OSPF, more adaptable, more capable, if you will. And here is an example ISIS routing table. As you take a look, we have our networks that it's learning here, what ports we're going to use to get there, and again, here's this like composite metric, if you will. Again, you look at a 10, that's a composite metric of adding in cost of all the links to get there, and then 115 for our administrative distance. Not quite as good as OSPF, but still better than RIP. EIGRP. I can't help myself when I hear this and I think of, McDonald had a router, EIGRP. I know, you'll probably never get that out of your head. But this was developed by Cisco as kind of like a hybrid, kind of the best of both worlds, best of distance vector and best of link state. Fast convergence time, low overhead for that, easier to configure than OSPF. And originally it was only able to be supported on Cisco, but other vendors have adopted this. So a lot of other vendors can actually use EIGRP. So again, it's trying to do the best of both worlds of the two. Here is a sample EIGRP routing table. As you take a look up here, D, there is your network, and there is that composite metric again. I get to this network via this port, this IP, and there's the metric of getting there. And again, 90 administrative distance is better than our other protocols that we looked at. So you're starting to see better information, better composite metric of so many routers away, so much bandwidth away to get there. And our last one, I believe this is the last one they mentioned for you, BGP, Border Gateway Protocol. This is the only protocol they mentioned that is an exterior. This is the one used on routers for your ISP, if you will. The routers for your ISP, so the protocol of the internet. This can handle multiple autonomous systems. Yep. A path vector routing protocol communicates via very specific BGP messages. This can be configured to follow policies, again, depending on the different customers and things you have. And this is your more complex one. It's really looking at different autonomous system numbers to identify networks. So it's kind of like, okay, here's an autonomous system number to identify hack. Here's an autonomous system number to identify Penn State kind of thing. And that one number represents the whole of hack's network. That one number represents the whole of Penn State's network, if you will. So it's really only concerned about connecting, one whole series of networks at one place to another whole series of networks at another place. And here's a sample BGP routing table. And as you see here, a little bit different information. It's like, okay, this network via here, and it's like, okay, this is actually subnetted. So therefore, actually, I combined two lines there. I'm sorry. Blah is subnetted, and it actually knows that it's connected to this port. So it's kind of like, hey, all of hacks, here's the information of all of hack's network. Here's the information of all of Penn State's network. It's that kind of thing that is maintaining. Alrighty, I'm going to come back in the next podcast and talk about some of the commands they have you use for dealing with some of these issues or troubleshooting.